right. This is very great pleasure to introduce Jane Gao. She is very well known for her outstanding contributions to random graphs. And today she will speak about the recent results on the sandwich conjecture. Please.
Thank you for the organizers for this conference. And it's a pity that we cannot gather together in Moscow because I was really looking forward to it. So hopefully next time. So today I'm going to talk a little bit about the story of random regular graphs. So this is based on collaboration with Mikhail Isaac from Monash University and Brandon McKay from Australian National, Misha from Monash University and Brandon McKay from Australian National University. The focus today will be random regular graphs. So I assume everyone knows about GNP and GNM. They are very normally referred to Erdős-Renyi graphs. Everybody loves those models because they are like vanilla type of random graph models. In particular, in GNP, all the edges are independent. So if you want to estimate probabilities of subgraphs, they are extremely simple. However, if you look at this random graph, the random deregular graph with the uniform measure, then everything becomes highly non-trivial. For instance, if I just ask you the probability of one match, if I just specify two vertices and ask you what's the probability that they are adjacent, well, you say that's not difficult. By symmetry, I should get E over n minus 1, right? But then I just conditioning, there's an edge there. What's the probability that another two vertices are adjacent? You can't get a trivial answer except from really counting the graphs, containing those two edges and divided by the number of graphs that has this edge present. So things become highly non-trivial, but nevertheless, there are still some tools for you to study those random graphs. If D is bounded, which means like 1, 2, or any constant, then typically you can use the configuration model to analyze properties of this G and D. This was introduced by Bosch in his very well-known paper and this becomes a standard tool for analyzing G and D when D is bounded. And when D is slowly growing with n, in particular, it has to be sublinear, then sometimes you can use switching methods to get probabilities of certain events or probabilities of edges, subgraphs of G and D. And when D becomes linear in n, then typically you can use Cauchy integral to count graphs, like deregular graphs or subgraphs of G and D. And that involves, the analytical tools will be involved. So that's typically the story, and the proofs are typically quite involved. And then that raised the question if it's possible to approximate the random irregular graph using GNP. Okay, so here is P equals D over N. And if you look at those two graphs, they look very similar when D is much greater than log n. So when D is much greater than log n, then GNP, when P is equal to D over N, it looks almost like a regular graph. But they're not exactly the same degree, but then the degrees are all asymptotically the same. So you can expect that a lot of properties will be shared between GNP and GND when D is in this range. And the idea behind is that I take a GNP, the random graph GNP, if you're conditioning on its degree sequence, then it has uniform measure. And that's exactly the GND, except here you really restrict the degrees to be all equal to B. So that introduces us to the sandwich conjecture raised by Kim and Wu in 2005. And I think it's a very beautiful conjecture. So informally, what this conjecture says is the following. I have my random graph G and D, and here you assume D is much greater than log n, as always in this talk. So the conjecture says that I can find P1 and P2. One is slightly smaller than D over n, and the other one is slightly greater than D over n, so that I can is a subgraph of this D random regular graph. And on the other hand, this D random D regular graph is a subgraph of G and P2. Okay, so these are random graphs, right? So what does it mean that one random graph is a subgraph of the other? So here's the formal description. You have to put them into, you have to construct a coupling to put those three random graphs in the same probability space so that this makes sense, containment makes sense. So assume D is much greater than log n. The conjecture says that there exists P1, P2, both asymptotic to D over n, and a coupling of three random graphs in the same probability space, such that if you look at those three random graphs marginally, then this low graph distributed as G and P1, this upper graph distributed as G and P2, and this middle graph distributed as G and D. But jointly, you have this containment with high probability. So that is what the sandwich conjecture says. Let me just stop for 1 second and ask if there's any question about the sandwich conjecture. Okay, here and now. So let's move to the progress in this solving this conjecture. So in the same paper that Kim and Wu raised this conjecture, they actually proved that there exists such a coupling where G and P1 is contained in G and D. 1D is much greater than log n, of course, and 1B is much smaller than n to the 1 over 3. But this side was not resolved. So you can actually put G and P2 here, where P2 is, same order as D over n. But what they proved is that it's almost contained in the G and P2, but has a small fraction of edges that are in G and D, but not in G and P2. So it's not a perfect containment. So in 2017, Dudek, Fries, Jinsky, and Sulaikis extended their result for the same kind of coupling, and it extends D from n to the 1 over 3 to sublinear n. And they also generalize this to random hypergraphs. So the containment part is the same. It's only for the lower part of containment, not the upper part. And more recently, there has been quite a lot of progress in the last year. So first, this is the is that Kim and Wu's conjecture is true for or D greater than n over square root of log n. So it try to take care of the dense case. Okay, for roughly speaking, for D, we also proved a containment, a perfect containment, but P2 is slightly larger than what we want. So what we want is P2 asymptotic to D over n, right? But we have some extra term over here. It's some function that that actually becomes 1 when D goes to linear in n, but I just want to put the upper bound here to make the formula a bit simpler. So roughly speaking, we have an additional term log n over here, which is not very ideal, especially in terms of solving Kim and Wu's conjecture. And then a bit later, in 2020, an archive paper appeared by Ryer, Uchinsky, and Slikus, they resolved Kim-Lewis conjecture for D, roughly speaking, greater than n to the 3 over 4. Okay, and they also extended the result to random bipartite graphs. And then I think these two papers appear similar time, just a few weeks or months apart, that I further extended the result over here with some twist of the argument, and it showed that Kim-Lewis conjecture holds for all D that's greater than log n to the 7th power. So this is already quite close to resolving Kim-Lewis conjecture. What we want is hopefully 7 can become 1. But currently the proof can't, the proof as it is can't really be improved to that extent. 7 is not optimized here. It's possible to improve to some smaller number, maybe like 4 or 5, but not to 1. And work in progress, that is a paper that we are still writing. Together with Isaac and McKay, we are extending this result to a sandwich theorem for near regular degree sequences. So here we are thinking about, specified degree sequence, D1 to Dn, and thinking about random graph G and D, with D replaced by this vector D. So we think about the random graphs with a given degree sequence. And if this D is a near regular sequence, which means all the degrees are asymptotically equal, then we should have exactly the same statement. The conjecture, Kim-Lewis conjecture, should also hold for near regular case. Okay, so we also confirm that, except here the condition log 7n would be replaced by some log n alpha, where this alpha depends on how near regular this degree sequence is. So in this talk, I'm not going to talk anything about near regular D because it's a bit more complicated to express, and the key idea is already carried in the proof for the regular case. All right, so why is it so helpful to have this conjecture? One thing I think is just beautiful conjecture, and it shows some kind of universality between different random graph models. But on the other hand, it's also very useful tool to study this random graph GNP. It allows you to carry information from GNP directly to GNP. So as a one application, let's look at the chromatic number of the random irregular graph. This has already been well studied. So actually by many authors, and I'm just listing the most up-to-date result. So for constant D, it is still an open question to really determine the chromatic number of random D regular graph. So the most recent result is by Iyer, and Greenhill in 2018, and they determined some of those values, the chromatic numbers for some specific, for some D, and then for the other Ds, they still are concentrated in 2 values. Okay, so let me speak this way. So for the chromatic number of G and D, it's concentrated in 2 values, but in some specific, for certain values, you can actually locate the chromatic number to a single value. And this one is a little, yeah, it's a little confusing here. What I really mean is a constant D, but letting D goes to infinity after sending n to infinity. Okay, so roughly speaking, it's for really large constant D. So it's by Courtois-Glenn, Maximiel, and Heatherich in 2016. What they proved is that in such regime, they asymptotically determined the chromatic number with 1 value. So they the asymptotic refers to b goes to infinity, and in that case, they can actually determine the chromatic number of G and D. So if you combine these two together, what it says is that if you want to list the chromatic number of G and D when D goes from 3, 4, 5, and all the way up, then you will see more and more, most of the, a lot of those places in this table, you will see two values over there. But more and more often, when D goes large, you only see one value. Okay, but it's still for constant regime, you can't. It's still very, from time to time, you will run into D where you can't decide precisely the chromatic number. However, in the regime where D does grow with n, here D actually is a function of n. So D goes to infinity, but D is sublinear. Then much earlier in 2002, Cooper, Fries, Reed, and Riordan determined the asymptotic value of the chromatic number of G and D. And in the linear case, Krivellevich, Sedekov, and Awamod in 2001 determined the chromatic number of G and D as well. So these two results, again, as I said, use very highly non-trivial argument. And now with the sandwich theorem, you can immediately determine the chromatic number of G and D by the chromatic number of G and P and translate it directly into G and D, as long as D is much greater than 7, where the sandwich conjecture holds. All right. And then there are more applications. Roughly speaking, any monotone properties can be transferred directly from GMP to GMD. And also, very often, the graph parameters for GMD, especially graph parameters that are monotone, for instance, for graphs, they can be directly transferred from GMP to GMD. And you can also study phase transitions in GMD using the phase transitions from GMP. For instance, if you fix a graph, balance graph H, and then study when does an H factor appears in GMP, now you can just study that in GMP, and then immediately an immediate translation can carry this phase transition from GMP to GMD. And another model that's studied a lot is bound population on GMD. You take a GMD, and then you preserve every edge with probability P. And then you get a new random graph, and you want to study properties of this new random graph. And now because GMD is contained is sandwiched by two GMPs, and if you bound population on these GMPs, you get another GMP. So bound population on GMD now is very simple. You can just study bound population on GMP, which is GMP. Okay, so having said that, so let me give you a little bit of an idea of how the coupling works. And I hope this is the only technical part, but really there's not so much math in there. I'm just going to explain the coupling scheme, and this coupling scheme has been used in the original Kim Fu's paper, and with a little bit of refinement in the later papers, but the key idea is kept the same. So what we are going to do is to have a sequential sampling of GMP and GMD at the same time. So to understand the scheme, let me first explain how you can sequentially generate a GMP. Okay, that's easy. So you just uniformly at random sample a set of edges sequentially, E1, E2, E3, E4, E5 to EM, uniformly at random and independently from the complete graph Kn. And then you just add to the construction of your graph G. What you need to do is choose this M to be a random variable, a Poisson variable mu, where mu you want to control such that by the end of the construction, the density of the graph is P. So it's very easy exercise to show that if you choose M to be a Poisson variable, then the final graph that you constructed is a binomial random graph, where this P relates to the parameter that you choose here as blue. Okay, so how about sequentially generating the randomly regular graph? Well, now I'm going to sequentially adding edges E1, E2 to En over 2. That's the number of graphs, number of edges in my graph. I'm going to sequentially adding to G with the correct conditional probability. So for every J between 1 and Bn over 2, I'm going to add this edge Ej according to the correct conditional probability, conditional on that the first J minus 1 edges has been added to my graph. Okay, so the first edge is just going to be the uniformly chosen from the graph because every edge appears in G and D with equal probability. And when I add the second edge, I uniformly choose one, and I want to add this edge to my graph with a probability that is proportional to the probability that this edge is in this G and D, conditioning on that Y is already in the graph G and D. Okay, and then I do it for every step. So every time I'm picking an edge with the correct conditional probability. So by the end of the process, I will get the G and D graph is the exact correct distribution. So now let's just put these two processes together. I'm going to uniformly sample edges E1 to EM from the complete graph Kn. And I'm going to construct or target to construct 3 graphs at the same time. These are targeted graphs. And when an edge is going to be added, say Ej, it's always going to be added to the upper graph, GMP2. And with correct probability, I'm going to add it to G and D. So I have to reject this edge Ej with some probability, such that the probability it is accepted is going to be this, right? So this is a normalizing factor. It's just the maximum of all those conditional probabilities, and therefore this probability is proportional to the probability that the Ej should be accepted by this process.
Sorry, Jane. Do you hear that for G of P2 on every step the probability of adding an edge cannot be smaller than the conditional probabilities that you need here? Or it can be?
Smaller than, can you say it again?
Yeah, so the question is, at every step when you add a new edge, is it true that for G of P2, the probability is cannot be smaller than for G of D? As far as I understand, you try to reject edges if in some cases. So does it mean that the probability for the upper graph is always bigger than for G of D or not?
Oh yeah. So in the upper graph, it's always accept. It's a probability with 1.
It's always
and in G and D, you want to reject with a small probability. And then in GMP1, you want to reject with some specified parameter zeta. So ideally, you want zeta to be bigger than the rejection probability over here, right? Then you can maintain the containment. So the problem will be resolved, which means the containment holds, if the rejection probability in this step is going to be smaller than zeta. So then every step I can maintain this containment. However, this can't hold if you want to construct the G and D this way to the end. And why is that? Just think about the last step that you want to add the last edge to the G and D. So you already constructed almost everything in your random graph, and there's only one edge left. So only U and V has degree -1, D -1, right? So you have the last step. All the edges that are still coming, they have probability 0, right? And only this one has conditional probability 1. So this quantity with high probability is going to be 0, and only this very minor probability that is 1. So in order to make this hold, you have to set zeta equals 1, which means P1 here has to be 0. And then you think how many steps I have to wait until I add this edge. You have to wait until the very end when all of those edges are tested, and then you finally reach this edge. So what effectively says is that if you want this coupling scheme to work until you construct this GMD, you have to have P1 equal to 0 and P2 equals 1, which is the trivial strategy, the useless one. Right. So what you can do about it is stop the process earlier. You will terminate after some random step, these steps. So here I'm going to use GTL, GT, and GTU for the lower graph, upper graph, and a middle graph after T step of the construction. I'm not going to wait until GMD is fully constructed, but I'm going to wait for these steps, and then I'll just keep output GMP, this upper and lower graph as it is. And then I just complete this GMT into a GMD using the correct conditional probability. So those steps, I don't add any edges to those graphs anymore. I only add the remaining graphs to GMT, to GT to complete it into a regular graph. So what happens is that by adding edges to GT, but not to GMP1, you will still have the containment GMP1 with a subgraph of GMD, but you can't keep this containment anymore. And that's exactly why in the previous results, you only have containment on this side, but not on this side. So I hope this is clear. So let's just wrap it up. How is this sandwich theorem going to be proved? We are going to choose D. That's going to be a Poisson random variable with mean mu, and mu is going to be chosen such that it's almost close to the completion of the random, the D regular graph. Just a little bit smaller than dn over 2. Okay, but there's still a small proportion of edges in the D regular graph that need to be completed. All right, and the next step is that we can prove that during the construction, the edges appearing to be added to the random regular graph, they appear almost uniformly. So every edge is still roughly with the same probability to be added to my GMD. In other words, the rejection probability can be bounded by some small quantity eta that vanishes with m. And now I can just choose another parameter zeta that is greater than eta, but the zeta is still little 1. So now by the end of the construction, what we will get is that the low graph is distributed as a binomial random graph MP1. And the reason is because of the mu is already very close to dn over 2, and the zeta is little 1. So what you will get is the P1 is going to be asymptotically equal to d over n, and moreover, this is contained in my GMD as a subgraph. Okay, so that's in the previous Kim and Bruce coupling scheme. So now how should we solve the other side of the containment, embedding GMD into GMP2? An easy observation is that we can do exactly the same by swapping the coupling part into its complement. So if you want to embed GMD into GMP2, it is really equivalent to embed GM y minus P2 into GM n minus 1 minus D, because this is the complement of GMP2, and this is the complement of GMD. Right? So now, again, I only need to, in order to prove this kind of coupling, I only need to prove the coupling scheme where I embed a random binomial graph into a random regular graph. But here, the only difference is now the parameter, because D, we can think about this little one, here is much closer to n. It's a dense case. In fact, it's probably a co-sparse case, and which makes the problem a lot harder. But anyway, we reduce the problem into a simpler problem that in both regimes, we only need to consider embedding a GMP into a GMP. Okay, so remember what really is required for the sample, for the coupling scheme to work is that we want to prove in this coupling scheme with high probability in every step, edges appearing or edges should be added to GMP with roughly equal probability. So if we look at this conditional probability, if I let S to be the subgraph of Kn by removing edges that has been already added to my graph, so it's Kn subtracting G j minus 1, and let T to be the degree sequence as the remaining degree sequence that for the edges to be added to GMB. So it's D times the one vector minus the degree sequence of G j minus 1. Then this conditional probability is exactly the probability that Ej, any particular edge, is in a uniformly random T factor of the graph S, right? So what we really want to prove is that for every edge in my graph S, they appear in a uniformly T factor of S with roughly the same probability. So really, proving sandwich conjecture is equivalent to prove the following problem, to solve the following problem. We are given a nice graph S and a nice degree sequence T, and then you let ST to be a uniformly random T factor of S. Can you prove that given any two edges, x, y in S, the probability that x or y contained in ST is roughly the same? And if you can solve this problem and solve the conjecture, I can agree. So when B is sparse, proving that you can contain a GMP1 in GMB is quite simple. So it's sufficient to consider S that is very dense. The complement is sparse. Okay, so it's called co-sparse case, whereas T is sparse. So in this case, we can just directly apply an enumeration result by McKay. And it will immediately give you the edge probabilities of this probability X in ST. So we explicitly express those probabilities and then show that they are roughly equal. So in this case, it's quite simple. How about the case that B is dense? So when B is linear in N and also the complement of B is linear in N. So in that case, we have to consider S as a dense graph and the T is a dense degree sequence. We went through this Cauchy integral calculations. So the probability that X is an edge in the T factor of S is expressed as the number of T factors of S containing this edge X divided by the number of T factors of S. And both of which can be expressed using a generating function. So just writing down the generating function for all subgraphs of S and extracting the right coefficients that represents the subgraphs of S with required degree sequence T1 to Tn. And then rewrite this using the Cauchy's integral. And then using saddle point, n-dimensional saddle point method. And there's not really much to say here. It's just very technical. But you can actually get the formula for these enumerating those T vectors, and then compare these quantities, get to the ratio, and then write down the probability that X is an edge. And then we compare, we can prove that all edges are appearing with roughly the same probability. So that verifies the Kim's conjecture for dense case density. So the really tricky part is the case where D is sublinear, and we want to prove the other side, right? So we want to prove that the G and D is contained in G and P, or in other words, we want to prove that the G and P is contained in G and D, where D is very close to N. So in this case, if we want to follow the same proof scheme, then you have to consider sparse graph S, where T has to be either sparse or dense. So in both cases, right, you have to prove both degree sequence T that can be dense or sparse relative to S. And we were able to solve the case where T is relatively sparse to S, but we were not able to express this probability when T is relatively dense to S, especially when S is very, very sparse. Currently, we don't have tools to study that. And that explains the gap that we had before. So for the sparse case, I'm not going to give any detail here, but we have to use switching method, but really consider very long switchings, and then also assume pseudo-randomness of S, and then actually prove that the S with high probability during the construction date satisfies those pseudo-randomness properties. And this explains this log n factor over here in our previous result. And it's just because we were not able to solve this problem for the dense case when T is relatively dense with S. So if you remember that earlier I mentioned the other group, Klimov-Sova, Ryer, Wojcinski, and Soakis, they actually were able to get tight bounds over here when D is roughly much greater than 3/4, right? So what is their idea? It's actually a very clever idea. They didn't try to express this probability directly, but they were working on the ratio of, x's in this T vector and y's in this T vector using switchings on this ratio. So somehow by working on this ratio, it is easier to get around with the kind of difficulty we had in our paper. And again, in their paper, in their proof, they also have to rely on pseudo-random properties of S for the switching method to work, but they only restrict to the regime where S has at least average degree at least n to the 3/4, so which makes it easier to describe the pseudo-randomness, and they only need to use short switchings. The type of pseudo-randomness is also different from what we require, and I'm not sure if it's possible to extend their proof when you make S much sparser. So this part I'm not very sure. So in the remaining 10 minutes, I'm just going to tell you our new fix to embed G and D into G and P tightly, even when D is smaller, okay, in the sublinear case. So what will happen is that we can, in fact, improve the coupling scheme. Instead of using 1 round of coupling scheme, we are going to use a 2 round coupling scheme. So the first round is exactly the same as what we used before, but the failed one. So remember, we said that we can't really, couple 3 simultaneously all the time until G and D is completely constructed. So still, we terminate around the same time D, and then by that time, we will get 3 graphs, right? This is target of G and D. And I still have a low graph and upper graph right over here. but I'm not going to waste it. I'm still going to use it. So now this first round of coupling is completed. This sandwich is tight, which means both densities of lower graph and upper graph is very close to the middle graph. So first, I'm going to embed this using the idea I described before by taking the complement. So embedding this is the same as embedding a binomial random graph Gn1 minus Q2 into the complement of HT. And this part can be done using the previous argument, and it's not tight, right? We cannot do it tightly. But the nice thing here is that eventually what we will get is G round I embed HT into some another random binomial random graph H now. And moreover, GU is distributed as a binomial graph GN1, and H is GNQ2. So even though this part is not tight, but I don't require, this Q1 is already Q1, Q2 together, because Q2 compared with Q1, it's much smaller. So when I add them together, it's still asymptotic to B over N. And by this way, I can get a tight sandwiching. So the miracle part here is really in those two rounds of coupling, there's obvious correlation between GT and GU because it's coupled, they are disjoint, and HT is again correlated with null. But GU and the GH null in the construction are independent. Okay, they're independent binomial random graphs, and therefore when you take union of two independent binomial random graphs, there's again a binomial random graph. And that's how we obtained a coupling of G and B inside another G and B, okay, where P is roughly Q1 plus Q2. Okay, so this is how this works. Is not in the graph H, then I'm always going to reject it. But if it is in H, then I'm going to accept it with the correct conditional probability. So here in the middle graph, I'm actually going to restrict that all edges added to the middle graph has to be in edge disjoint from the output from the first round of the coupling. Whereas in the lower graph, it doesn't matter. I just look at every edge that comes, and I reject with probability zeta. So it's the same as in first round. Okay, so because every edge is independently adding to the low graph with probability 1 minus zeta, it's independent of the output in the first round, and that way we can get independence this way. So a very rough idea. Independence is implied this way, but the containment is not going to maintain anymore. Okay, because you obviously will have edges that are added here because it's not in H, but it's going to be rejected over here. But for the proof to work in this stage, you only need when you take the union of GT is the edges that has been output in the first round, it is still maintained. This kind of containment is still maintained. That is sufficient for the proof to work. So we modified with slight twist of the argument. We just add another round of the coupling, and it allows us to complete the coupling scheme. All right, so it was just in a very brief manner that I explained how the coupling works, and I just want to spend a few minutes to talk about open problems that remains. So Kim-Flu's conjecture is for all B much greater than log n, and we only managed to prove, as I said, with some power of log n, refinement of the argument can still be done, but I don't think it can be reached to be much bigger than log n. So it definitely still requires new ideas to really prove this conjecture. Another conjecture, I think many people know about it, but it wasn't written anywhere, so we just put it in our previous paper with this chemical conjecture, the sandwich theorem. So what it says is that if you take two integers d1, d2, where d1 is at most d2, then this g and d1 is a subgraph of g and d2. That you can couple them such that g and d1 is contained in g and d2 as a subgraph. I think it's a quite natural conjecture, but we are not sure if when d1, d2 are constant, if this conjecture is true. So in that part, we are a little unsure, but still we sort of feel that it is correct. So this conjecture is widely open. Currently, what is true is known is when d1 is 1, then d2 is 3, then by symmetry, you can easily prove that this conjecture holds. And the other case is when d1 is at least log 7n, and the d1, d2 is, the difference is sufficiently large that we can just use the sandwich theorem that we proved to prove this conjecture, right? So because you can embed g and d1 into some g and d, right? And then into some g and d2. So the distance over here is just to ensure that you can find proper g and d in the middle of g and d. The other case is when d1 is not too large. It's smaller than n to the 1 over 7. You can actually prove that any pairs of d1, d2, this conjecture is true. And this is done by studying. It's a different argument. So roughly speaking, we can lift this condition when d1 is not too large by studying the number of perfect matchings in the deregular graph. But I believe that this condition can be significantly relaxed with more effort, but probably going to be hard to be completely lifted. So how about for constant b? Why I said it's we are not completely sure is that when d1, d2 is constant, it is actually known that you have this kind of arithmetic. So you take two independent copies of g and d1 and g and d2 minus d1, conditioning on that they are edge disjoint. Okay, so then take those two copies and then take the union of those. You get a d2 regular graph, right? So what this random graph actually is contiguous to the uniform model, which means anything happens almost surely over here is also holds almost surely in this random graph model. However, this contiguity doesn't really imply the sandwich theorem, the kind of coupling that is required. So so somehow it makes you feel that probably it should be true, but we don't really know how to approach for constant degree over here. So that's something I feel quite interesting. And the other thing is for non-regular, I mean, not even near regular degree sequences, this is still open. So with my students, we managed to prove similar coupling where you can contain generalized GMP, here P replaced by some a matrix. So it's not the homogeneous GMP anymore, and then that contains in GMP. D now is a vector. Okay, in the case where D is sparse, we are not able to prove this part. We are not able to prove the dense case either. It seems much more complicated in the non-regular case. So in the end, I'm just going to briefly mention the limitation of sandwich theorem. So it's very useful. It allows you to translate a lot of results directly, but still there's limitations. For instance, non-monotone, non-convex properties can't be directly translated. But maybe it's still can help you to to deliver some information, but at least it can't be directly translated. Another thing is distributional results typically can't be translated. If you want to study the distribution of random variables, you can't deduce it directly from GNP to GND. In particular, subgraph counts are typically much more concentrated in GND than in GNP. Just because you don't have the variation caused by the difference of the number of edges, right? Especially for large subgraphs. So the picture for distribution would be very different. So in particular, if you're interested, you can try to study even the variance of the number of triangles. I think Brandon one time asked me about this. I think it was quite interesting. So you can, in some sense, really study you can get edge probabilities and so on in GND when D is pretty large. I think, say linear, right? You can get edge probabilities, but you can't really compute the variance because the error is too big. So all the leading term got cancelled, and then what remains is the error term. I think that currently the best bounds, the variance of the number of triangles, you need B to be smaller than n to the 2/5. Okay, and then when B is greater, is not true to actually compute the variance precisely. So those problems are still widely open in the study of random irregular graphs, and you can't really get such information from sandwich theorems. All right, so that's what I want to talk about today, and thank you very much for your attention.
Thank you very much, Jane, for the very interesting talk. Are there any questions? I think that we are out of time, but maybe one or two short questions. Okay, I have one. So are there any results on making these asymptotical relations between P1, P2, and D tighter? So can you say in some cases for some good D that the error terms between P1, P2, and D are very small, and for some bad D they are not so small?
Oh, the gap between the sandwich. So what we proved is that there's some gap, but it's not the best. So we know the gap can't be, the gap has to be much greater than d to the -1/2. That's just because of the degree variation, right? So here is GNP, GNP2, and then here's your GND. And then if you look at the variation of the degrees in GNP1 and GNP2, they are both asymptotic to D over N.
Yeah.
So you need the square root of the variance there, deviation there. So it just has a natural lower bound on the gap that must be there. And what we proved is a little bit better than (1). I think it's something like 1/log(n) or something like this. In different cases, it's a bit different. So, but roughly speaking, it's about 1/log(n). So there's definitely room to improve, and I think it could be useful in some situations, especially if you want to translate distribution. We thought about this. I'm cheating a little bit here to say that you can't translate distribution results. In fact, you can say, if the distribution satisfies such and such, then you can translate. But the such and such is so restrictive that we can't find an example of counting subgraphs that satisfy those conditions. Then, therefore, we cannot translate in any meaningful sense. because we don't even know what kind of cut satisfy those conditions. But if you can shrink the distance between them, you can relax those conditions, right? And maybe in some really rare cases, you can translate the result. But still, most cases, I believe, you can't really translate the distribution results.
Yeah, thank you very much. Okay, thank you very much, Jane.
Thank you.